And welcome to my presentation on circuit synthesis-based matching network design using Microwave Office. I will start with a brief introduction. I will first bring you a very short motivation on the topic. Then I will continue with matching network design technique where I solve the double matching problem. This is more or less a theoretical part of this presentation, but I want to show you to understand the method. And then I will bring two examples where I design a power amplifier, a broadband power amplifier using Microwave Office, and a second example, a more sophisticated topology switch mode power amplifier, which is intended to be part of a digital transmitter. And I will finish with a very short conclusion. In communication systems, high efficient broadband power amplifiers are often desired because if you have high bandwidth, you can use it for example, multi-band operation, to do it with a simple amplifier, and you don't have to put more to cover a lot of frequency. Okay, yeah. High efficiency values are always desired because if you have high efficient power amplifiers, you have low power consumption and therefore you save a lot of money in the operational costs. But if you want to build a high efficient power amplifier, you have always a trade-off between linearity and efficiency. So the most efficient, or if power amplifiers with the highest efficiency possible, are generally switch mode power amplifiers. So design based on small signal S parameters is not possible if you do such a design. So you have to use different designs, such as using a transistor model or load pool based designs. But if you have described your transistor using a model or a load pool design, you end up always in a double matching problem. So you have to design a matching network for the input and for the output of the power amplifier. So this is generally not feasible to do this in an analytical manner, so you have to find some computer-aided design process, and this we'll discuss in the next session. As you can see here in this block diagram, this is more or less the simplest one to show a power amplifier, where I have the transistor in the middle and the input match and output match. So you have to design the output reflection coefficient for the input match and the input reflection coefficient for the output match in some way to make the desired operational mode of the power amplifier. So for the design, you consider this matching networks as lossless equalizer. This is, for the technique I will present, necessary. So as I said before, you can't do this in an analytical manner, especially if you have very high bandwidth. So you need computer-aided design process, or as it turns out, very beneficial is to do this with an optimizer-based solution. And one of these is the so-called simplified real frequency technique, or SRFT, which I will present next. It is very beneficial if you do a design for a power amplifier or matching network in this case with transmission line based, because they have a high quality factor and therefore low losses. And if you consider such a transmission line with an arbitrary length L, you can terminate it with an impedance ZL. You can write the input impedance like this equation. But this is not very handy because you have the tangent in there, so it's nonlinear in terms of the length and frequency, and also complex. So if you apply the so-called Richard transform, you can set the J tangent beta L to the Richard variable tau. So you end up in a rational function for your impedance, for your transmission line terminated by an impedance. And this is very handy because you can put a rational function easy into any optimizer or computer-aided design process. And this is again true if you use two transmission line with equal length in the series connection. So you can again write down the input impedance as a rational function. And this can be done for any arbitrary number of transmission lines, as you can see here, as a more or less normalized and generalized version of this input impedance. And because you can do this for the input impedance, you can also do this for the input reflection coefficient. And so you end up as a description using two polynomials, h of tau and g of tau. And because we consider this as lossless, and reciprocity is always true for transmission lines, you end up in a full S-parameter matrix. This is called the Belavich form. And this is described in more or less three polynomials, g of tau, h of tau, and f of tau. And yes, so you can easily put it into an optimizer process or any other computer-aided design process because it's easy to calculate on polynomials. And this is where the SRFT comes into place. This is done in an optimization process. So you start with the polynomial h of tau, which has first to be initialized to any number. So then, because then you can calculate f of tau, which is only determined by transmission zeros at DC. This will you know because you have either a high-pass or low-pass topology for your matching network, and the number of unit elements. So because you have h of tau, f of tau, you can use the losslessness condition and reciprocity theorem to calculate g of tau. So you have the full S-parameter matrix S of tau. So, and because your transistor is known, because of load pool measurements or a model or anything, you can calculate a gain over this whole power amplifier. And this is denoted here as g of omega. And then you can define a cost function with your gain subtracted by an arbitrary target gain, which is again what you design for amplifier design. Put the magnitude of this, and then you have an error function e of omega, epsilon of omega, and this is minimized in the optimizer. So you optimize h of tau, calculated the gain, and then do that so long until the e of omega is 0. And then you have, if the optimizer reaches a minimum, you have described your matching network, and then the last part you have to do is to calculate the impedance. This can be done by a Richard extraction. So and for a power amplifier, this is done in 2 steps. You design firstly the input match and then the output match, and so you're done. And the good thing about this methodology, because it's very flexible. So I did this to implement this whole optimization process in MATLAB. This can be done by using a least square nonlinear optimizer. And the thing is that you can design your cost function in any arbitrary manner. So it's very flexible. You can use several different power amplifier topologies or any kind of that. So you can define it as you like, or if you, depending on your design problem. So, and you end up in a very flexible solution to do such matching, to solve such double matching problems. So, and now that's enough for the theory. I will start with a first example. The goal is to design a broadband power amplifier, which is based on a Cree-Garnhampt, the CG8410F. In this case, this is only a simulated design. I will come to an actual built one in the next design. So I used the model for the design this in here. So the goal is to design a power amplifier which have at least 65% of power added efficiency and at least 10 dB gain over a frequency range from 2 to 3 gigahertz. So quite high bandwidth. So the design flow is done as follows. Firstly, the SRFT is implemented in MATLAB, and the calculation of the gain is done in Microwave Office. So I have here a schematic for the power amplifier, which I will show in the next slide in more detail. And there the gain is calculated, read out by MATLAB. Then in MATLAB, the optimizer run is done, and then the schematic here is changed all the values for the impedances for the power amplifier. And so again, if the optimizer reaches its minimum, a design can be done. So the schematic looks like this, where you have the transistor model here, biasing networks, subcircuits for the input matching network and the output matching network, which consists of transmission lines, the T-line elements. And these variables here are accessed by MATLAB and changed in the optimizer run to find determine the performance of the power amplifier. And then over this circuit, a simulation is done in a measurement. A gain and power added efficiency measurement is carried out in the simulation and then read out by MATLAB, and a cost function is generated which is minimized. So, and after that, the SRFT calculates following impedance values for input and output match, and the matching network were done in a stepped impedance topology, as you can see here. This is mostly because they have very low insertion loss, so they are very and easy to build. And if you draw down the S22 of the input match, you can see here in the red curve, and S11 of the output match is this here. For here fundamental frequency and harmonic frequencies. As you can see here, I didn't consider that in the first place. I only do the optimization. So again, you end up in somewhat like reflective harmonic termination, so you get a more or less harmonically controlled amplifier by this technique. So, and here the performance of the PA, you can see that you have a gain from 11.5 up to more or less 13 dB, which is higher than 10, which is good, and efficiency from around 70%, power added efficiency, of course. So this is more or less a simulated result, but it shows you the power of these design techniques. So now, in the second example, I will show you a more sophisticated design topology, which is a power amplifier, which is intended to be part of a digital transmitter. So now, in a digital transmitter, to carry this out first, if someone doesn't know it, how it works, you have a digital input signal. In our case, we generated this input signal with pulse width modulation, PWM. So you end up in a rectangular shape input signal, which is very beneficial to exploit switch mode power amplifiers, so they can operate in a highly efficient manner. I can see here the power spectral density of this input signal, which is more or less the issue of such power amplifiers, because they have energy over a wide frequency band. So this is from 0 to 5 gigahertz. Center frequency is 2.5 gigahertz. So this is a huge bandwidth. This signal is PWM modulators can generate. You can modulate each kind of input signal. In this kind, we used an LTE signal, which is here, this small part in the middle, which has 20 megahertz of bandwidth. And now this is the big issue, because if you use that power amplifier in a transmitter, you have to get rid of all those quantization noise, which is added by the modulator due to this rectangular shaped input signal. So you have to place somewhere a filter at the output. And you can do this in two ways generally. Firstly, you use an absorptive filter, which is shown here. So you use a circulator and normal reflective filter, and all those energy in the side lobe is reflected by this filter in the stop band and terminated into heat. This is the most easy way to do so, but the efficiency is quite poor. And there's also a second solution to connect the filter in a direct manner towards the matching network. But the filter would influence this matching network severely, so the efficiency or the operational mode of this power amplifier would be anything but what you desire. So you have to design your matching network in a way to consider both the transistor's performance and also the filter. And so you end up in a few design issues. And firstly, as I said before, the filter influences the matching network severely, and also you have a high signal energy in this filter stop band. So this is quite tricky. The design here is again based on Cree-Scarnham, the CGH410F, and in this case the optimum impedances for this transistor were carried out in doing actual load pull measurements. And the design of the matching network is done in microwave office. And this brings you again to a broadband double matching problem, which was solved using simplified real frequency technique. And here you can see the design flow. Firstly, we used our lab setup to carry out load pull measurements. The measurements describes you the behavior of the transistor. Then the calculation of the matching network was done in MATLAB. With the calculated impedance, the matching network was designed using closed form and solutions EM simulations using XM. Then the matching network was realized and built in our rapid prototyping process in our lab. So here you can see the results of the load pull measurements. Firstly, on the right side you have the results, which is for output power used with continuous wave excitation at 2.5 gigahertz, which is intended to be the passband of the filter. So you see a classical load pull contour with maximum power at this here, and if you move away from this optimum termination, the output power decays in looks like a cone. So you may have all seen this. But what's more interesting is outside the performance of the transistor regarding power consumption. You can see here on the left a load pull contour for drain current, again taken out by continuous wave excitation at 2 gigahertz in this case. So you can see that the drain current is severely is lower here than here. This is by more than a factor of 5. So you can use terminations which are basically better for power consumption than other terminations. So because the drain voltage is constant, so this drain current equals the power consumption of the transistor here. So based on these load pull measurements, some optimality criterion has to be defined to build this amplifier, to design your cost function for the optimizer process. So and there was more or less the straightforward solution to have maximum output power in the passband of the filter and limit the power consumption otherwise. And as you can see here, this was done by this cost function. You calculate the gain depending on the termination frequency, subtract the target gain weighted by the input signal's power and an arbitrary weighting factor here, minimize it, and otherwise outside the signal band you do this by minimizing weighted drain current depending on the termination and frequency. And this is done by considering, as you can see here, by the input signal, the behavior of the transistor and the filter. And when you do this optimization process, you end up in several different realizations depending on the weighting factors. And one of these you can see here. It was again intended to do a stepped impedance topology because it's easy and has low losses generally. But the problem is here you end up in very low impedance values, like in the third element 0.75 ohm, and very high, which 460 in the sixth element. So, and this is not possible to do this with transmission lines. So for a first proof of concept, I tried to do a mixed design and add up some capacitance to the lines to realize very small wave impedance and add inductors to realize these high ones. And this works perfectly well, but you add up some losses. Here you can see the matching network and the input reflection coefficient of the matching network and the filter combined. So you have a very well termination at the passband, which is here in the black curve. And outside the signal band, you have the terminations for higher frequency move up there, and for lower frequency again here. These are regions with the very low power consumptions for the transistor. And if you build this and measure it, as you can see here, input match, output match, biasing and the transistor, you end up in a perfectly working switch mode power amplifier, where you have as output signal this RTE signal with a little bit of nonlinear distortion add up by the transistor and power amplifier, and all those quantization noise in the side lobes is gone. So it works. And as a second try, I also tried to remove those high losses, so I end up in a design using radial stubs and some interdigital structures to add up this, to build this low impedance transmission lines, which also works again very well. So now, at last point, I'll finish with a short conclusion. I presented a design methodology for broadband power amplifiers, which is, with this methodology, you can solve the double matching problem for very high frequencies. This is a computer-aided design process and done with optimization using MATLAB, or you can implement it in any other design language you like. This is a very flexible solution because you only have to design your cost function in the optimization, and you can even use microwave office to calculate your gain or efficiency of your amplifier as you want. So, and again, I presented 2 examples, a broadband power amplifier and also a more sophisticated one for a digital transmitter. So, thank you for your attention.